Okay, so very good evening once more, and welcome to this class on tensor analysis to my channel Physics for Students. And my name is Shaunak, and I welcome you all to this, live classes where we are actually learning more about tensors. Oh, okay, fine. So there is one person, I think one of my subscribers who has already asked me, hello, sir, kindly recommend books on tensor analysis course. Thanks, Malik Usama. So, Malik Usama, what I would request you just be in the line for a second. I would definitely recommend you a book. I would say that you can better go to my, I would say, channel where I have actually suggested not only one book but a series of books. And from there, you can find out whichever book is suitable because tensor analysis again is a very big, wide area. Now, which part of tensor analysis you're looking? What is your mathematical background? Are you looking for an advanced analysis or something not? I will just hold on for a second. Just trying to find the video link which I can give it to you. Tensor analysis. I think it made a year back. Yep. So here is the link. I think this will give you a fairly good idea about tensors. So Malik Osama, if you're listening to me, you can very well go and watch this particular video, which will give you a complete idea how to start learning tensor analysis. I mean to say everything regarding that. So what we would start, we actually started last yesterday only. We came into Tensor, who was basically the founder. We also engaged in a wonderful discussion, learning about breaking the myth about Marcel Grossman, etc. And subtle is the Lord. I showed you that Grossman was individually, helping to transfer things from one frame of reference to another. Okay, so just a second, hold on. Just have a glass. Yeah. So what we will start today, just be on the line. I just need to check on one more thing. Yeah. So what we need to do today is that now that we have already got a fairly good intuitive idea in terms of understanding what are tensors, what it is, who was the founder, how things would actually takes place from one to another, we would do today what is that we need to understand that what is called a coordinate system transformation. Now, as I was telling you that the transformation equations are something very central, and we need to have a very good what we call the transformation system. And this transformation, yesterday I also told that it has nothing to do with the relativity as such. It can be related to any engineering, mechanical, or any part of the area of physics and science. So first we would understand a little bit about coordinate transformation. Then mathematically, I'm going to show you about coordinate transformation. Another important thing which I already shared with all of you, there is I have got another channel which is called General Relativity Explained. Now this is a general relativity tensor calculus. See, this is the link which I have given. If you can see this, I have given it in the chat box. Space flight player, right? If you can say your name, it would be great. So if you learn general relativity, the basic tensor, so I mean to say, obviously there are books on general relativity mathematics itself, but general relativity tensor calculus itself, I need to check. But if you overall learn tensor calculus, then you can learn the general relativity itself. If you have missed my earlier classes, space flight, I would request you to go ahead and watch it, because what we are trying to do in this series of classes is to get hold of the understanding of tensor itself. And I cannot find any book which is very specific to the general relativity part, but overall I think understanding of tensor calculus itself will give you an idea, because all those things are covered. Metric tensor, stress energy momentum tensor, Riemann curvature tensor, manifold, parallel transport, everything whatever is required in GR are covered in the books of calculus. I mean to say tensor calculus or tensor analysis. So if you do that, you can. And yes, what I am doing also in this series of lecture is that I'm trying to give you those books or those lectures which are very much related to general theory of relativity. So you will find me talking about tensor calculus, again shifting to general relativity, because that is the core idea. So what I was telling is that you can go back to this channel of mine. I would request you. Uh, it is not the same as this channel, although you might find few of the lectures to be same. But remember, I made this channel almost, it has been a year. I know that I am busy with this channel and other works. I could not make this channel grow. I mean to say, I cannot post much of videos, which I have started off lately. There also I am taking live classes, especially on general relativity, and I'm starting with Maxwell's equation, many things which you won't find in this channel. So this is a channel which is meant for, yes, space flight. This is a channel which is exclusively dedicated to general relativity. No other things, no other discussions will happen in this channel. If you are only interested to understand general relativity, you should go to this channel. And here you will find many explanations slowly, which is not related to physics for students. This channel is an overall complete understanding. Anyway, so let us go back. We don't have much time. So you see, we have explored this one. So space flight, I would recommend you to learn tensor calculus itself. I've already given that link. Automatically, you will find a shift towards general relativity. Yeah, Dhruva, very good evening. Dhruva is a very nice subscriber and a very attentive listener, and give question. This part we have already done, so I'm just skipping this part. What we would be interested with is this. So you see, with this part, kind of a vector, if we take, then we solve a wide range of problems in physics and engineering, right? And they actually provide a foundation for understanding tensors. What? The vectors. So here you see what happens is that vectors are objects with components that transform between coordinates systems in specific and predictable ways. Now, if vectors or components are objects with components that transform in a very specific and predictable way, that means what we are doing, we are specifying rules. Again, I would say right on the top, you can see we are specifying the rules. So vectors are objects with magnitude and direction, that is known to us since class 3. And vectors can have more than one kind of component, and those different types of component are defined by their behavior under coordinate transformation. This is very important. Those different types of component are defined by their behavior under coordinate transformation. That means what we are going to do is take a different kind of an approach. We're going to see how the vectors in different coordinates takes place, and then how the components change, and from that components we will go to the tensors, because tensors are same thing, the components keep on changing, and we will define those rules, then we are done. So I always believe that us take an approach where we know, and then from the know we should go to the unknown rather than jumping into the unknown. Okay, so here you see what I am trying to explain to you, just to have a patient understanding and listening to this. So first thing is that what happens, okay, let me quickly put apart from this part of the, okay, fine, then let it this be. So what happens, I would say, when you change the coordinate system in which you're representing that vector. For example, I ask you that, yeah, physics code, very good evening, very good evening, very good evening. Just a second. So what happens if I ask you that a vector, when you're changing the coordinate system in which you're representing the vector? So Dhruva and physics code would answer, sir, nothing happens. And you are absolutely right, right? So nothing at all happens to the vector itself, but the vector's component may differ in the new coordinate system. You all agree? And the purpose of our lesson slowly is to develop, understand how these components change. And once we understand how these components change, we will be able to understand what? The tensors. So I always believe to take a known approach and then go to the unknown. Now, here is a basically kind of a diagram. What I have trying to tell you, you are looking at this diagram and trying to explain. So here you see that, for example, I would say if you change the coordinate of a system. Now, for example, whether you measure a temperature, say for example, this room, right? If whether you measure the temperature of this room in Celsius or in Fahrenheit does not make the room feel hot or cold. Absolutely agreed. It doesn't make you feel hot and cold. Now, we also should remember that vectors are mathematical representations of physical entities. And what are those entities? Those entities do not change because you change the coordinate system in which you are representing. Okay, let us think in this way. Does the size of a room change if you tilt your head in one side? Okay, let me see. You are clear with this, right? The vector itself, so whether you measure it in Celsius or Fahrenheit does not make any change, does not make it feel room hotter or colder. Now, first concentrate on the left-hand side of the diagram. Don't go, because these are all animations, somehow streamier because it cannot support animation. I have to explain you one by one, but it is good. Rather than animation, we should pay attention to the orthodox method of learning. I mean to say the usual way of learning. So my question to all of you is that, does the size of the room change if you tilt your head from side to side? Obviously not. But if you use your tilted head, so for example, the right hand side of the diagram, if you use your tilted head to define up and down, okay, then what will happen? The points that you designate as up and down, or the top on the bottom of the room, will change. And this will not change what you call the height and width of the room. Absolutely. Physics code is absolutely right. So room doesn't change under such. So on the right hand side, you see if I draw the XYZ direction, what is going to happen is that the important idea is that the top and bottom of the room may change, and this will change what it won't change what you call the height and width of the room. So the basic idea is that the room itself does not change, it remains invariant. Again, I repeat, it remains invariant under such change of coordinate system. And say, for example, if you define the center of your head, say, for example, from here, okay, center of your head to the origin of your coordinate, then walking towards one wall will offset the room. But once again, the XYZ value of locations within the room might change. But once again, the room will be unchanged. So similarly, as you see, I have shown in the diagram that there is a sofa, right? A sofa cum bed. The dimension of the room in inches rather than meters will only allow you to put the numbers very big in real estate, or maybe you can hold a bigger sofa. That's it, nothing more. So from this slide, or from our discussion right now, we can understand that if coordinate systems transform, say for example a rotation, a translation, or maybe a pulling apart, that is scaling, leaving physical quantities unchanged, what exactly does happen when the vector of a transformation coordinates change? Now, in order to understand that, we have to look into this part of the. Okay, no, I would say, okay, just a second, I will open my Jamboard, and I have already done my homework for you people. So I think that will be there. Today is what, 28th of November, right? Right. Okay, so I will go to the Jamboard. I think Jamboard actually is much clearer in terms of understanding. If you do a little bit of homework, I think it is an excellent thing. I was thinking of purchasing once what we called this pen tab for writing, etc. But then I told them my handwriting is absolutely horrible, so it won't do. Okay, so you can see all this, right? Now I would like to explain this part of the illustration. So for example, this particular part of the figure, right? So here you see in this transformation, the location of the origin have not changed. That means this part of the origin has not changed. It has remained the same. Sorry, take a thicker pen. This part of the equation has not changed. So what has happened is that the location, it has not changed, but both the x and y axis has been tilted in a counterclockwise direction, this x axis and this y axis. And what it has resulted is this theta. Sorry, this theta, this angle, right? I mean to say this one and this one. So again, I repeat, I'm taking a slow approach. Please don't get angry on me because I'm constantly repeating certain things. This is my way of teaching. In this transformation, the location of the origin has not changed, but the x and the y axis has been tilted counterclockwise, as you can see, and it has created an angle theta. So the rotated angles are basically the x prime and the y prime. Okay, rotated axes are x prime and y prime, and I have used this dash in order to tell that this is a little bit different from others. Now, next is that what impact or what change does this I would say rotation have in the vector space. I would like to put it in this way so that it becomes clear to you. This is my question to the next part. So it has moved and it has not changed the origin, but it has tilted from x prime to y prime. That's fine. And now question is that what impact does this rotation have on a vector in this space? Now, in order to know that, we have to go to another figure, which is this one. Okay. Figure 1 and figure 2, I mean to say, I have drawn both these figures so make you understand. So don't need to worry, we will go slowly one by one. So we have got a figure A and we have got a figure B. So these are the two. So the vector A and its components in both the figure A and its components, let us take a note, those who are watching this live class, is that the rotation has no effect on the main vector. The rotation has no effect in the main vector. I am just drawing it a little bit longer so that you can understand. Is it clear? So the main vector, it has not changed. So the main vector has been the change. So let me repeat it. The rotation has no effect on the length of the direction. At first, it looks a little bit different, I understand. But as itself, if you look at the length or direction of A, it has not changed. Okay, but the rotation has made a change. What change it is? The rotation has clearly caused the component of A to change to A prime X. Now I will reduce this. This is caused to A prime X, this one. Okay, the rotation has caused a change of the A to A prime X, that is the X prime component of the A in the tilted coordinate system. X prime component of the A in the tilted component system, and Y prime A prime Y, which is shorter than AY. Can you see this one? This one is longer. I've shown this in my generativity video. This is shorter. And let me erase this one also. So you can see this now clearly that this one is shorter than this. I hope things are going clear and fine. So what we see from here, that the rotation has caused the component A to change to A prime, A to change to A prime X, the X prime component of A in the tilted coordinate system. That means it is longer than A prime X. This is longer than the A prime X, and A prime Y is shorter than AY. So where is my marker? A prime Y is shorter than AY. Now, if we continue to rotate, I mean to say, if we continue to rotate like this and this and this and this, if we continue to rotate the arrows in the same manner, if we continue to rotate just like the way I'm rotating her hand, what we will find eventually is that the A will lie entirely on the X prime axis. A will lie entirely on this X prime axis, this one. If you continue to rotate like this, like this, like this, I mean to say, you're rotating, right? So what will happen? If this is the base, right? And if continues to rotate, let me show my hand so that it will become a little bit clear. So if this is the base and I'm rotating this, it keeps on rotating, rotating, rotating. So ultimately, this will match. Are you getting my point? It's rotating, it will match. So what is going to happen over here in our diagram? In this diagram, what is going to happen is that A would vanish, right? And what is going to happen over here? Let me put it in the text. I don't know whether it will happen or not. Yeah. So here you see, if I put A prime Y will be equal to 0. Okay. This A prime Y will be equal to 0. Because it will slowly mix and we won't have the A prime Y. Okay. So what we can see from here, we can understand that eventually reaching at an angle in which A lies along the X prime axis, at which the Y component the vector A would vanish, and the X component would be equal to the A component, and AX again will be equal to A. So from here it will happen that AX, I mean to say A sub X, will be equal to A, because here it will happen, it will lie over here, right? It will lie over here. So it will become to A, as simple as that. So what we can tell from here actually is that finding the change of the components of a vector, we are trying to find the change of the components of a vector due to rotation of the coordinate axis, can be done using this type of a graph. Okay. Now, if you think that, I mean to say, about change of the axis in the figure, this one. Okay, let me show you the figure, this one. Yeah. So you also realize that the vector component a prime x in the rotated coordinate system cannot depend entirely on the ax. So I mean to say some part of this part will remain over here because it has rotated. Some part of this will become over here. Okay, let me remove this because it is too cumbersome. I mean to say those lines should not be there, so you can get a clearer view. Fine till now. Okay. So from here, what do we do? So we now move to the next part. Okay, so now I will show you something else. But before that, I would like to tell you that what now we are doing is that uh, the portion of A that we have used had previously been pointing in the original Y direction. I would like to magnify and show you in a different way. What is that? Okay, let me show you this one. Okay, so this is another figure. I'm going to say this is actually a zoomed one, this one. That means it has been actually rotated. Okay, this is, I know it is becoming too a little bit difficult to visualize, etc. So the A portion, this portion, the first portion of this figure shows how the vector component ax in the original, okay, let me point it out with the pen, then you can understand this ax in the original, that is the non-rotated, I would say, system contributes to the A prime x. How much of the AX contributes to the A prime x in the rotated system? And in the B portion, the portion shows how much of AY, this component, this part of the component in the original systems contributes to the A prime x of this component, this part. So from figure 1 and figure 2, we can find out that how much of the AX in the non-rotated coordinate system is contributing to the A prime X in the rotated component system. And the B figure shows how the vector in the AY original coordinate system is actually contributed to the AX in the rotated system. So from non-rotated to rotated, and this is how it happens. So as you can see in both the figures, there is something which is called L1 and L2. This is the L1, sorry. This one is the L1 and this is the L2. So what we can say is that in both portions of the figure, that is A prime X can be considered as made of this. This is the A prime X. You get it? This entire line. Let me show you. This entire line. This is considering of two parts. One is the L1 and L2. So can we not tell that this would be equal to this? Is it clear? Again, let me again repeat you, because I know the figures are a little bit small. Maybe you're visualizing through watching through mobile, etc. So what we can see is that if we see the figure A portion, again I am repeating it, figure A portion, this first figure, what we can see is that the vector component of the AX, the non-rotated, this is non-rotated, this is the rotated, the vector component of the AX in the original non-rotated coordinate system contributes how much to the A prime X? Contributes means when it gets rotated, how much the change, etc. happens. Okay, so the figure from the AX coordinate system contributes to the A prime X in the rotated system. AX is the original non-rotated system, contributes to the A prime X non-rotated system. So what we are doing is that we are going from the non-rotated to the rotated. That is always rotated, always will be used by the prime sign, this one, this sign. So be rest aware. So again, I repeat, the portion of this figure, the figure A part, left hand side shows that the component AX in the original non-rotated coordinate system contributes, that means makes a change in the A prime in the rotated system. And the figure, this one, this B figure, actually shows how the vector component of the AY, let me remove with the duster. I call it as a duster. In my college, I've got a duster. Here it is a big problem. Yeah. So where is this? A prime Y, this one, this portion, how much of the A prime Y, again in the non-rotated system, contributes to the rotated system, that is into the A prime X, this part. So because of all those which we have seen, again, let me remove it. it comprises of these two, because a prime x and etc. This entire line has been taken by one L1 and L2. Then we can definitely tell that this a prime x, that means this line, okay, comprises of L1 and L2. This comprises of L1 and L2. Okay, good for as of now. And to determine how these segments depend on AX and AY, I will use this kind of a triangle. As you can see here in this is a triangle. You can see this. Okay, here you see is the triangle. Okay, I will try to make it a little bit bigger for you. Oh, no. So let me remove this and bring this forward. Here you can see the triangle clearly. Here you can see I'm so sorry. Yeah, it is showing the triangle clearly. Yeah, you can see the triangle clearly. Okay, so when you see this triangle clearly, what I'm trying to tell is that you can see that there is a hypotenuse of a right angle triangle. Let me show you with the marker. So you've got an hypotenuse of the right angle triangle, which is the AX1, this one, this is the right angle triangle. Okay, this is the right angle triangle. And what we see over here is that the right angle triangle has an axis called alpha 1, 1. Where it is, just a second. Oh, I'm so sorry. This should be removed. This one should be brought forward. Just a second. Just let me reduce it. This one is got an alpha 1, 1. So this is the triangle. This one, and this one. Okay. This is alpha 1, 1. Okay. Let me take you this to the fresh page so that you can understand things better. Okay. Yeah. So sorry. Yeah. Let us put it over here. This is much clearer, right? So what we see from here is that this figure has got a triangle, which is the hypotenuse, and it is a right angle triangle, and it has got an axis. I'm sorry, it has got an angle, which is this alpha 1, 1. This one. I can write it as alpha underscore 1, 1. I mean to say just a convention. I mean to say we are using this as a metric notation because we will use it in the tensor. First row, first column. Okay, first row, first column, that means 1, 1. So the length of L1, that means the projection, this length of L1 would be what? I have to take that from this slide. That means I have to basically take the cos theta, right? I've already given over here. Yeah, now you can see. Okay, this is a better figure, right? So here we have got alpha 1, 1. I have written it as alpha 1, 1 first of all, because this will be again very useful for our understanding of tensors. And we will get here as ax cos alpha 1, 1. Quite simple. Now, in order to find the length L2, say for example, this one, what we will do, here it is. Again, we will go here. This is the L2 part. And what we get from here, that in this case, the triangle, you can see this is the triangle. This is the alpha 1, 2. This is the alpha 1, 2 angle. And from here, we will get L2 as what? We will get L2 as this one. AY. So this is the AX. That means I'm depending on the x-axis, this one, right? This axis. And here I am going to this Y, this one. So this would be A prime Y cos 1, 1, and that would be cos 1, 2. So this would be cos 1, 1. This would be cos 1, 2. Simple. And this alpha 1, 2 is basically the angle which is formed by A prime X and A prime Y. And hence, what we can do is that we can add these two angles together and we get a value like this. Okay, we can add these values together. I mean to say, if we really want to add now this portion, this L1 and L2, what will we do? We will simply add this one and we will add this one. So that is what I have done in the fresh board. I've added these two things. So what we are trying to, I mean to say, what this particular exercise, what it has helped is that how we can, through the transformation and the movement of angles, how we can actually gather the values. Now, until and unless we understand these things, tensor calculus would be difficult. So you see from the rotation of the components, how one component changes, how the angles really change, and how things really happen. This is how we take into account. Now, you should note one more thing, that this new component A prime x that we have found is called a weighted linear combination. Okay, so what do we mean by weighted linear combination? This is actually what I have shown over here. I think it is better shown on the side. So what is a weighted linear combination? We all know that it is basically a combination where you are combining several values of w, say for example w1, wx1, then the w2 component of x2. So that is what it is called, weighted linear combination. And why it is called weighted, you see I have explained over here. The term weighted means that each is assigned a weight, I mean to say a particular value. And the term linear is because it is obviously linear combinations going the same way, so it maintains what is called a linearity. So we means to say that if you have values say a and b and you combine them together, then it will be by adding the values of a. So this a prime x is basically a linear combination of ax and ay. Okay, so we will take a pause over here today, and we have first taken step forward slowly to understand how the rotation of the axis actually can be combined together. Okay, and what we will do in the next class is that this a prime x and this y component can be again rotated. So we can get again a prime y equal to a x cos alpha 2 1 and alpha 2, and from there what I will show you in the next sorry, yeah, this one, this actually this equation, I mean to say this equation can be then later taken into a form of a matrix, nice matrix, I mean to say row column, and this I will show you tomorrow in the next class. I'm not going because I will lose my hours also, because StreamYard has got less number of hours. I need to download this OBS, which I don't know. So tomorrow we are going to take this angle formation, this simple equation, and we will form what is called a transformation matrix. And that becomes very central idea of a tensor, because in tensor also you will form the transformation matrix. That means the rules of transformation from here and there will form into a nice matrix, and this matrix carries the form of a tensor, be it a metric tensor or whatsoever, to rank 2 tensor, rank 3 tensor, 4-dimensional tensor, 2 by 2 matrix, whatever. It will actually, so eventually what is happening, from vectors we are moving to the vector components. Number one, these vector components are transferring from one point to another. They are making different angles, trigonometric angles, etc. So we are assigning these vectors components together, and we are creating a value. We are creating an equation. L1 plus L2 makes up a complete equation. And from that equation, we are going to see that how we can create a matrix. Why we are creating a matrix? Because definitely with row and matrices, only if you form a column and a row and then it will create a matrix, then we can assign that matrix and create a safe house for tensors, because tensors look like matrices. If you see 0 0 1 0 0, it's what it is, a kind of a 2 by 2 or 3 by 3 matrix. That means somehow from this coordinate system of components, we have to include those rows and columns in such a way that a beautiful picture of a tensor comes forward. So I hope you have liked today's lecture. I have just started slowly building one by one, and it's going to take time. I mean to say, let us not rush. We will take time to explore, but ultimately our objective is to learn tensors, be good, and learn the other areas of physics which are carrying tensors. Thank you very much. Please do put up your comment also here. I will be back same time tomorrow at 9 p.m. on this channel, Physics for Students. Don't forget to like and subscribe and share the video as much as you can. Let others also run from this. Thank you very much.